Hello, everyone. Good afternoon. Yeah. My name is Daniel, and I'm from TI-PDS team. And in this presentation, we will introduce a new DC-DC topology called trans-inductor voltage regulator. So, we can call it TLVR for short. That's why. And And in this agenda, I will introduce the background and the motivation, what is deriving this need for the new topology. And then I will introduce the topology and about the operation principle of this topology and how it works, and then go through some practical considerations, and finally I'll make a conclusion. By the way of this background, we can see here the application we have discussed in this presentation is about the device in CPU, GPU. GPU is the graphic processor unit and all the ASICs. So traditionally, this device will be powered up by the multiphase buck converter. But as the technology of this converter of the GPU CPU continue to develop, so they have new requirement for this converter. It's a next. We can say that in particularly the current is putting higher and higher, but the supply voltage and the operating voltage is still remain to 0.7 or 1.0 watt, and so. When the current is very high, and the operating voltage is still keep the same, so it is very challenging for our device converter. So as you can see in the in this slide, this gives a projection of the microprocessor consumption, power consumption. So we can see in the next couple of years, the power consumption will go even faster here. And we can see that traditionally this power consumption is driven by the silicon technology. Yep. And this is true, but most recently we can see that there's a new architecture called the chiplet. The chiplet architectures, essentially the chiplet architecture means that divide all the parts, the different function parts, like this CPU, GPU, and this ASICs, different parts into pieces, into different dies, and co-package them in a big package here. So the designer can output a new power IC as quickly as possible. And this one, in this presentation, we are talking a lot about the transient response. So it is very useful here, and we will start understanding the challenge we meet here in the multiphase buck. So in this slide, I have a block diagram here. And this is the load. The load means the CPU, GPU device. And this is a DC-DC converter. Then we can see that there is a low pass LC filter here, and we use this part. Here is to filter the output current. It means we will get the output voltage ripple smaller. And another thing is decoupling the load from the converter. Here, we marked the load current here. The load current, we marked the I load. And the output current of the DC-DC converter, we marked we labeled the I sun. And for this one, if we want to make a low undershoot or overshoot, the key thing is that we need to make the I step, the slope of the I step as quickly as possible, right? And in this equation here, we can see the relationship between the output voltage deviation, the output deviation voltage here, and between the output voltage deviation, the step, this one, the step, and the Cout, the output capacitor, and also the slope here. And we can, from this equation, we can see the challenge we have met here, because the step is getting very bigger and bigger, but the deviation voltage, the output deviation voltage is getting smaller, and the output capacitor is getting more and more expensive. So the challenge here, is this, the slope. We need to increase the slope of the I sun. And before we go to the details about the TLVR, in this picture, in this slide here, this is really what the TLVR do for us. And we can see that the TLVR will enable a faster I slope here, than the multiphase buck. So just like we use the small inductance value here, and but the TLVR to achieve the thin load transient, the TLVR will have much lower capacity here. And this one we will talk about how to derive the TLVR topology here. TLVR has been introduced in 2019. So this one TLVR is Buck-derived topology. It is optimized for the faster transient response. And we can see here, TLVR is a loop transistor on the cap-inductor buck converter. So we can see that this is the multiphase buck, this is the TLVR. And for TLVR, we just replaced the output inductor here to a coupled inductor here. And another thing is that we put the secondary winding of the coupled inductor in series. And then we used a compensation inductor here. This compensation inductor here is used to control the co-efficiency of the TLVR. So when does it make sense to use the TLVR? So this I recommend that when you use the higher phrase count, so I recommend it is larger than six phrase. But if you use low phrase, it is also possible. And you can also see here, if you need the high DVDT load transient or the moderate, not the minimal, and it's just the moderate voltage ripple here, you can use the TLVR. As I mentioned before, the TLVR is similar to the traditional capacitor inductor here. And first we will cover the operating principle of the capacitor inductor. So you can see that the capacitor inductor, the winding is just have one single core here. And also you can see that the typical couple efficiency we need to do is about 0.5 to 0.7. And you can see how it works. If the primary current in this winding will induce another winding, another current here in the second winding. So this is the key point. This is the key point. The current in one winding will influence the current in another winding. So this is the key point. We should remember this. And another thing is about this traditional capacitor inductors that they have some flaws here. You can see that it is this is just the two phase here, and if we extend to high phase like this, this four phase here, and if we just use this architecture here, this here, what we can see that the coupling coefficient for this leg to this leg and this leg, they were not equal. They were not equal, and that means this leg coupling to this is this to this, this to this, this to this. But if the current is important from this leg, it means the current will go to this or go to this side. So the coupling coefficients will be different. So and another flaw challenge for this is about if we wanted to realize the equal coupling coefficients, we will get a very complex geometry to maintain this. Yeah, the geometry is very complex. But for TLVR, TLVR is rely on the indirect capacitor inductor. You can see here, they used a shared current here, in the second winding here, They use this winding here to do the couple. So this is just the indirect coupling inductor, but this is the TLVR, what we used now. We can see that there is a compensation inductor here. Why need this one? So for this one, if the coefficiency is very high, there will be a very small leakage here. And also for another phase, there will also very small leakage here. So if without this coupling compensation inductor here, just like this, the current in the primary side will be very high. So we need to use this we need to use this capacitor inductor here to limit the magnetic current in the primary side. And here we can see a conventional inductor here. This is from Eaton. We can see that the primary side and the secondary side is in parallel. This is in parallel here. So we can design the multiphase buck and the TLVR in a single PCB. Just if we want to test the efficiency of the multiphase buck, we just can disconnect this the LC inductor. Then the TLVR converter tends to be a multiphase converter. Now we will get into more details about the operating principle of the TLVR. This slide here shows a four-stage of the four-phase TLVR design. 1, 2, 3, 4, four-phase TLVR. And the most important concept to realize here is that the primary current from each phase is the sum. The primary current is the sum of the magnetizing current and the LC current. This is very important. And the switching state of each phase influences the voltage across the LC inductor. So we will go through the operating states to see how the phase current at primary 4, how this current is derived. In the phased states here, we can see that only this MOSFET is on, and the other phase, the top side MOSFET is off. So we can get the voltage in the magnetizing inductor is V in minus 4 V in minus V out. And for other phase is just about minus V out. And then we add all the voltage here. So we can see that the voltage at the LC inductor is about V minus 4 times V out. In the state 2, we can see that all the MOSFET is off. All the MOSFET, the top side MOSFET is off. So we can get that the voltage on the magnetizing inductance is minus V out here. So we can get the voltage here on the LC inductor is minus 4 times V out. And in state 3, this one, we can see that the phase 1, the MOSFET is on, but the other MOSFET is off here. Then we can also get the voltage on the LC inductor is also about V minus 4 times V out. But for the magnetizing current and the LC current here, we can see that this is the current for the phase 4, And in phase 1, in state 1, the magnetizing current is up, and then it's keep down. But for the LC inductor here, we can see the voltage is this. So we can see that the LC inductor current is, the frequency is about 4 times the switching frequency of each phase. So another thing, we can see that the I prime 4 equal to ILM plus the ILC. So through these two cave, we can get this one. This is the I prime 4 current. And this is about the transient step. Here is about the transient step up. Wait a second. And this one, when the load is step up, we want when the load current is step up. So what will the controller do is to make to turn on as many phrases as possible to response this load transient here. And for generality, we cast this on phrase and on off phrase here, and here we can use the voltage. We can use the voltage we get from this one to calculate the slope of this inductor here. So for the multiphase buck, we can say that this loop for the buck it is equal to the this is TLVR. This is not phase buck, but we can say that it's just equal to this loop buck is just equal to each phase magnetic current to the sum of each current of this magnetizing current. But for TLVR, what we mentioned before, that the current here is equal to the magnetizing current plus the LC current here. So we can get this. The sum equal to this. So we can get the equation here. The difference between the multiphase buck and the TLVR is that the TLVR will add this one here, and this is proportional to the n total here. It means that if the phrase count is larger, and this one will, and the slope for the TLVR will even larger. And what we can see, this is the step down for the TLVR. The process is similar. And for this one, for the multiphase buck, is also this one. The voltage here is V out, is minus V out. And for the TLVR, the voltage here is, there are two parts of the current. This is magnetizing current, and this is LC current here. So we can also get that, this equation. And what we can see is that the current, the slope is related to the square of the n total. So it is very, it's very interesting that when the TLVR will step down, it will be much faster, even even much faster than the freeze spark. Here, we do a simulation here with the same input and output voltage, the same load, the load step, and the same output capacitance here. Also the same inductor here. But we can see the difference here. The difference is that for the multiphase spark, the response time is about 3 microseconds, and for TLVR, it is just 1 microsecond here. And also for the overshoot, also for the undershoot for multiphase spark, it is about 1, 2, 3, 4. It's 4 grid, but for the TLVR, it's just 2 grid, half of them, right? And another thing we need to notice is that the voltage at the LC inductor. We can see this overlap, the PWM overlap here. The PWM overlap make the LC inductor makes the voltage of the inductor this. It builds up. We can see that if this overlap is more, and we can see that the voltage of the LC will even higher than the input voltage. So this is why the LC will slope very quickly. Yeah. And then this is about the simulation of the load step down. We can see that, yeah, the step down, the response time is 10 microseconds, and for TLVR is 2.5. This improved a lot. Yeah, and also the overshoot for TLVR and for multiphase spark and for the TLVR here is about 1/3 or 1/4 of multiphase spark. Another thing, we will introduce a new concept here is about the DC load line. The DC load line can help to reduce the output capacitor, but first I will give the definition of the DC load line. And when we design a converter here, we will put the output voltage first. When we design the converter, the converter will have a minimize and maximize minimum and maximum output voltage here. So normally we just put the output voltage here is in the middle of the minimum and maximum output voltage. So half of the window for the overshoot and half of the window for the undershoot. That means the DC load line, the impedance of the resistance of the DC load line is about 0. This is what. But if the resistor of the DC load line is not 0, what will happen then? We can say that when we load up, the output current will drop. From the idle one to the full load value, and when the load down, this output voltage will jump up. Yeah, this always should here. So all we can see is that the undershoot for this two is the same. So we can get that this differential voltage from this to this will be smaller than this one, right? Will be smaller than this one. And this is what we do for both TLVR and multiphase back, because this is the same for the both two designs. But one thing we need to notice that if we use the DC load line, the output voltage will reduce just a little here. 5 minutes left. And here is about the LC inductor. The LC inductor is an AC inductor. What we can see from this, when the transient frequency is low, transient frequency is very low, we can see that the LC inductor jump up, and finally they will decay to 0. And this is the constant time for this for the LC. But actually, in TLVR, it works in high frequency, right? So the current, the LC current here, cannot decay to 0. And is there a risk here? No risk. This is because that the load up and the load down makes the current in the opposite direction. So the current, the inductor will not saturation. And this one is what we care about most. Is this is the efficiency between the multiphase buck and the TLVR design, and this efficiency is get with the same parameter listed here. We can see that it too is nearly the same. And we can see that even at the heavy load, it is just about 0.1% lower for the TLVR design. But in practical, we do not use the same parameters here for multiphase buck and the TLVR. And to achieve the same transient response performance, the multiphase buck will get a very small inductance here. The inductance for multiphase buck will be smaller. So the ripple in the multiphase buck inductance will be higher. So actually, the efficiency for multiphase buck will be a little lower. So in practical, the efficiency of this two is nearly the same. And about this one, for the efficiency, we will introduce another concept about the dynamic phase shielding. We can see from this efficiency, from this curve, and when the output voltage is larger than 100 ampere, the efficiency is nearly the same. That is because we do not enable the DPS, and when the load current is lower than this, lower than about 75 ampere, if we enable this DPS here, the efficiency will be much higher. And this one, we give another example here is a apple-to-apple design here. In the former simulation and the former ones, we just use the same parameters for both multiphase buck and the TLVR. But in this design, the two converter use the same spec. The same spec. That means the load step is the same. What we can see is that for the output capacitance here, the total output capacitance for TLVR is just 4.4 millifarad, and for multiphase buck is 7.7 megafarad here. And what this makes about 45% reduce in the output capacitance here. And also we can see that the 100 microfarad ceramic capacitance is we do not need this expensive capacitance here. So the cost for the TLVR will be much lower than the multiphase buck. And then we will go to the practical consideration of the TLVR. And here is about the LC inductor selection. I believe this is a new concept for most of us. And for this one, typically we just select the LC inductor between 1 and 1.25 times the LM. So this is we just select this from the beginning, and we will adjust this one. Adjust the value of the LC inductance according to the efficiency and according to the load transient performance here. And what we can see, another thing we can see that I need to, here. The switching frequency for this converter is just 600 kilohertz. This is a 8-phase TLVR. So the frequency for the LC inductor is 4.8 megahertz. And another thing is that the RMS for the LC is just 2.8 ampere, but the ISAT for this LC need to be this. It's very high. It's very high. Yeah, and another thing we cared about the TLVR is about the output voltage ripple. In the left side, this is a model. This is a model about the ripple. We can see that the I3 current goes through the PCB impedance and the capacitor network here, and finally go to the load. Finally go to the output capacitance, and then transfer to the output ripple. So we can see the difference between multiphase buck and the TLVR is that for TLVR, the LC inductor value is added to each phase of the primary side of the primary phase. So this current cannot get cancelled. But for multiphase buck, the magnetizing inductance, the magnetizing current can cancel. But for the TLVR, it cannot be cancelled. So what we can see here for the 12 to 1, 12 to 1.2, 12 to 1.8, the ripple for the TLVR is about 3 or 4 times that of the buck converter. So is this a big problem? not always, not always. And when people use this TLVR, what the concern about is the transient response. Yeah, and if people want both the transient response and the output ripple, what we can do? So, yeah, we can just use the interleave TLVR. We can, yeah, if the phrase for the TLVR is enough, we can divide them into two, this part and this part, to make this interleave. And another thing you can see, this is the PWM, the odd number, and also the even number. We make the odd number in this list, the even number PWM in this list. We can see that the PWM is here. To make an interleave here, an interleave here. So with this method, we can get a typical approximate one-fifth times the one-fifth of the output before we use the interleave. And then it's about the layout of the typical power stage here. And this one is the power stage, and this one is the TLVR inductor here. We can, as we mentioned before, the current for the LC inductor is very high, right? When they load up, the current is very high. So, so the trace we received for the LC current here, I recommend this, the width of the trace is larger than 50 mils. This one, 50 mils. And this is the layout for the real one, and this is the load, the MCU, and this is the interleaved phrase. This is CD2 phrase design, and this is just half of them, and this is another half. Make an interleave here, and the controller is here. The controller is here, at this part. So, so we can route the signal here, because this is a power trace beside the at the each side of the load. So we can route the signal from this one and this one to route the signal. To route the signal, yeah. And here, in the past couple of years, and TI have proposed mainly optimize the controller and optimize the power stage for the TLVR. And this is the part number here. And also this is another part number here. And so if you want to use TLVR, and so we can, okay. Sorry. If you want to use TLVR, you can contact us for the devices and for the controller and for the power stages here. Finally, we will make a conclusion. We have introduced the TLVR topology and how it works, and how. And another thing is that we can get how the TLVR will reduce the output capacitance than
multiphase block. And then we introduced some practical considerations here, and finally we proposed some optimized component here for the TLVR. So that's all. Here's the reference here, and you can download from the chat.com. And yeah, that's all. Thank you.